Okay, sometime in the next few minutes, this is going to finish, and it's going to pop up, and it's going to look weird. So just ignore it when it happens. All right, let's do another one of these. I am going to give you some to do today before we leave, but I want to try to give you something a little more challenging first. Kind of see some of the algebra that we're going to run into. How bad do we want to go here? Pretty bad. Let's try this one. Same instructions. Here's the function. F of x equals, I'm not sure why it keeps doing that. F of x equals cube root of x minus 1 over the cube root of x squared. Now we've got an interesting function here. Let's do this on the interval 1, 8. Should we look at the graph or no? Just get down to the work? Get down to the work? Okay. First thing, is this a continuous function on the closed interval that we are looking at here? Well, these are cube root functions, right? Both of these are cube roots. The cube root of a number is always defined, isn't it? Whether it be positive or negative. So we don't have to worry about negative numbers. We do have to worry about that second one on the right, the right side. We have to worry about division by 0, and that can happen. Where does that happen? When x is what? When will we get 0 down there? If x is 0, right? Is that in our interval? No. So this is going to be a continuous function. And we have a closed interval. So let's go ahead to step 1. Let's find the critical numbers and then evaluate the function. So our derivative. Well, before I get the derivative, let me rewrite this as powers of x. It's kind of an exaggerated 1 there, isn't it? Try that again. So is that minus x to what power? Negative 2/3. Good. All righty. Now the derivative. Is everyone okay with that one? Okay. Derivative now is 1/3 x to what power? Negative 2/3 plus 2/3 x to the what? You see it? Negative 5/3? Okay. Questions? Now that's what we've done up to this point in this class, right? Take a derivative, we're fine. But now it's part of a bigger question, right? It's saying what's the absolute maximum on this closed interval. So now I have to go further, and I have to ask myself the question, when is that equal to 0? And I have to ask myself, when is that undefined? And it's these two questions that are going to create all sorts of chaos for us. First, let me try and set this thing equal to 0. How would you like to go about that? Or do you even want to? Not really, but you have to, right? My instinct here, I don't like the 1/3, 2/3. I'd like to clear the fraction. I'm just going to multiply everything by 3. All right, and that would give me, I can do that because it's an equation, right? Anything else I can do? Take out an x to the 2/3, positive or negative? How do you want to do it? Negative x. We got to be careful here. I'm doing as instructed, but x to the negative 2/3. Then what would be in here? That's what you're saying do, right? You could do 1/3. What do you do when you, how do I say this? Like when you take like x cubed minus x squared, you factor out an x squared, and then you put x minus 1, right? And you put an x there because that's really a first power on that, and you're going to add the powers to get your 3 back. So if I did this, I need to make it so that I get back this, which means I'd have to put what? What do I put here? 1 plus 2 times x to what power? I need it to be able to add up to be what? Negative 5/3. So x to the negative 1 equals 0. Do y'all agree with that? I like that. That's not the way I was going to do it, but I like it. Okay, times multiplication there, right? We've turned a sum into a product, and that means we've factored it, which means now I can set each factor equal to 0. Now that I've got some kind of easier looking equations, let me rewrite what they are with positive exponents. Y'all agree with that? What can I do on the equation on the left? Say again? Think about this. And this is going to turn out to be a very important fact that everyone in this class needs to be aware of. Let's just take a little step to the side here. Let's say I tell you that I have a fraction. And let me say that that fraction equals 0. What can you tell me about A? The only way that a fraction can ever be 0 is if A is 0. Because I can always multiply both sides by B, can't I? And that would cancel your B's, and that would still be 0, so that would force your A to be 0, right? So let me write this down. I mean, that's what's happening, but this is a fact. All right? A fraction can only be 0. Only equals 0 if the numerator is equal to 0. It's the only way it can happen. So when you look at this fraction over here on the left side, the only way that's going to happen is if the numerator is 0. But the numerator is 1. So what does that mean? Is 1 equal to 0? No. That means there's no solution to this. That equation over there. There's no x you're ever going to be able to plug in over there that's ever going to give you 0. Why? Say, right? I mean, do you agree? Let's pick any number you want. Now, if you plug in 0, it's going to be undefined. But there's no number you can plug in that'll give you 0. But what about the equation on the right side? Can we get a solution for that? Yes, we can take the 1 to the other side. we can multiply both sides by x and then change signs. So x is what? -2. But what are you going to tell me about -2? It's not in the interval. The interval was from 1 to 8. So we're screwed. Not in 1/8. All right, now I still have to consider one more thing. I kind of did all that work, but let me scroll back up here. I'm looking now back at this. Where is the derivative undefined? So when we look at our derivative, is it ever undefined? Maybe it'll help if I do this. Isn't that the same? Isn't 1/3 x to -2/3 the same as 1/3 cube root of x squared? The other one is that on the right? Is that ever undefined? You ever going to run into any problems with that? If x is what? 0. But 0 is not in 1/8. So I don't have to worry about it. That means I have no critical numbers. So I have nothing to try, nothing to check. So I move on to step 2. What's step 2? Plug in the endpoints. So I want f of 1 and f of 8. That means I want the cube root, what was it? Cube root of 1 minus the cube root of 1 squared, and then cube root of 8 minus cube root of 8 squared. So cube root of 1 is 1, cube root of 1 is 1, so 1 minus 1 is 0. Then this is going to be 2 minus 4, which is -2. Well, I only have 2 answers, so step 3 is just to compare them, figure it out. So what's my max? What's my min? 0's max, and where does it happen? 1, right? And the other one is at 8, and that gives me a minimum of -2. So it turns out that this function, the absolute max and mins, occurred at the endpoints only. Is that all right? I wanted to show you this example because the algebra in there was a little bit more challenging, right? I mean, there's just, to set it equal to 0 required some work. Pardon me? Oh yeah, can't get around it. Well, you can graph it to check. That's fine, but you've got to do the work. Okay, x square root of, yes, yes, yep. How far back? Oh, right there? Was it? Oh, did we forget to put it in the? Oh, it was. They were both negative, weren't they? No. Hold on. Let me go back. Oh, yes. Thank you so much. I didn't have the original function from you. Both of these are 1 over, aren't they? Go. Well, that's terrible. Let me just erase this. It should be 1 over the cube root of 1 squared. This one should be 1 over the cube root of, what is it? 8 squared. Man, I'm glad you brought that up. That would have been so wrong. Because the original function was x to the 1/3 minus x to the negative 2/3. Good call. 2 minus, what is that, 1/4? So denominator is 4. Which is 7/4. Which changes this. Well, it changes everything, doesn't it? Because our max and mins are backwards now, aren't they? Please fix that. Who caught that over there? Who? You didn't say anything about it? Myra, right? All right. You get a bonus more for just, questioning. I mean, we're all human, right? So, all right, I think we're good now. All right, back to the next one. 16 minus x squared on the interval -1, 4. Everybody have it? I'm actually going to take a look at this one. So we have x times the square root of 16 minus x squared. And we're going to look at it on the interval -1 to 4, right? 3. Here it is. So we should get, it's looking like we're going to get an absolute minimum at an endpoint, right? And it looks like we should get an absolute maximum at a critical number, right? Where a derivative is 0. That's what it looks like we should get. But how are we going to do it algebraically? So is it continuous on that interval? Yes. This function right here is defined between -4 and 4. Okay, you can't... No, I'm saying the function itself is defined on that. So to look from -1 to 4 is within the domain of the original function. So we are continuous. And we are closed. And so we are in business. First step is a derivative. What would you like to do here for this derivative, folks? We're going to have chain rule mixed up with what? Product. Here's product right there. So the derivative of this will be the derivative of the first one times the second one plus the derivative of the second one. That's a chain rule, isn't it? Square root of something. The derivative of square root of something is 1/2 root of the something. Okay, continue with chain rule times -2x. That's the derivative of what was inside the root. Am I done? Times x. That finishes off the product rule. So here's where we are. 16 minus x squared minus x squared over square root 16 minus x squared. What happens there? What happened there? 2's canceled out, right? These 2's canceled out. I put my x and x together, got x squared. It's negative, so there's subtraction between the two now. And see, in the past, we've been pretty much okay with this, hadn't we? Like we'd be, okay, whatever, we got the derivative, we're happy. But now we have to take this thing, set it equal to 0, figure out where it's undefined. So my first thing is, where's this derivative equal to 0? Next thing I'm going to do is figure out where the derivative is undefined. Or does not, where does the derivative not exist? You already set that equal to 0? Ready or not? Here we come. The good thing about having an equation is we can multiply both sides of the equation by anything we want, right? So how could we clear the fraction out? By multiplying both sides by what? Square root of 16. Now, how many of you would want to just move that negative x squared over root 16 minus x squared to the other side first? Yeah? We could do that first if you want. Just move it over. Becomes a positive x squared. So there's no cookie cutter way to do these problems. Anything that you do, as long as the rules of algebra are maintained, it's okay. So that was a legal move. Now, multiply both sides by the square root. So I'm multiplied by the square root of 16 minus x squared here. Square root 16 minus x squared here. On the right side, they cancel. On the left side, they're the same, aren't they? So root of something times the root of something, the roots go away. All you're left is with the something underneath. So 16 minus x squared equals x squared. Move x squared over. 16 equals 2x squared. Next. Yeah, let's divide by 2 first, and then now we'll come in and take square root. So you get square root of 8. There's two answers, right? I should write them down. X equals root 8. X equals negative root 8. Now, do these numbers live inside of our interval? Oh, wait. No? No? What's our interval? From negative 1 to 4, right? What is the square root of 8? 2 point something, right? So it lives in there, doesn't it? How about negative square root of 8? That's negative 2 point something, right? That doesn't live there. Only the positive one lives there. Not in negative 1, 4. The other one, though, is. So we do have one critical number, don't we? So far? Now I need to come back up here and ask myself where this thing may not exist. So is your derivative ever undefined? Well, didn't we say earlier the original function, at the very beginning, didn't I say the original function is defined between, negative 4 and 4, right? The original function is defined there. If you pick any number bigger than 4, like let's say 5, you get 16 minus 5 squared, that's negative number under the root, right? Same if you pick negative 5. When you square it, you get 25. So we're stuck. Our original domain is between negative 4 and 4. So when we come back down here and we look at the derivative, this guy right here is also stuck between negative 4 and 4, right? This one's stuck between negative 4 and 4 also, but wait a minute. If we plug in 4, what would we get? We plug in 4 right here. Wouldn't we get division by 0? We would, wouldn't we? So x equals 4 or x equals negative 4 causes our derivative to be undefined. Negative 4 is not in the original interval, is it? Right? Remember, we're between negative 1 and 4, so I can scrap negative 4. What about 4? Is that in our original interval? Yes. But what can you tell me about 4? What are we going to do in step 2? We're going to plug in 4 anyway, aren't we? I mean, 4 is an endpoint. So we can either do it now or we can do it in step 2. The fact that it's the same number, what's that? Yeah, we're going to do that also. We're going to do that right now. But I'm saying, remember step 2 says plug in the endpoints, and they're negative 1 and 4. And we're saying right now that we need to check 4, don't we? This right here is telling us we need to check 4. But we're going to do it in step 2 anyway. So this is an endpoint. I guess that's what I'm saying. This was an endpoint anyway, so we're going to get it. If it turned out that it wasn't an endpoint, then we would have to check it. So let's just be precise. We'll finish this up. Here's me checking. I need to figure out what f of root 8 is, and I need to figure out what f of 4. We'll go ahead and do it now. And that's going into the original function, which I forgot. Oh, no, now I remember. So it'd be square root of 8 times square root of 16 minus, what's the square root of 8 squared? Just 8, right? So we get square root of 8 times square root of 8 again, right? Because 16 minus 8 is 6. Or 16 minus 8 is 8. Root 8 times root 8 should be 8. And if we plug in 4, we get 4 square root of, 16 minus 4 squared, which is 0. Isn't it? So we're looking at an 8 and we're looking at a 0. They correspond to the x values of root 8 and 4. So I'm ready to go to step 2. Anybody have a question here? Okay, when I go to step 2 now, what I need to do is check the endpoints. I need f of negative 1 and f of 4. But I already know f of 4 was what? 0? So I don't need to do that again. That's what I was saying just a second ago. F of negative 1, though, is negative 1 square root 16 minus negative 1 squared. That's negative 1 square root of what? When you square negative 1, you get 1, so minus 1, so square root of 15. So negative root 15. Which is like, what, like 4 point something? Negative 4 point something? So what about max and min here? What's the biggest value my function takes on? 8, right? Happens at root 8. What's the smallest value it takes on? At negative 1, it takes on the value of negative root 15. Any questions? Sure? I'm just going to go back to this graph. One way I can check this is just taking this and asking it to plot the point, what was it, square root of 8, 8. And that should fall right at that top point, right? There it is. Kind of small, but did you see it pop there? So I'm pretty happy about that. And then the other one, I mean, we know that that's the minimum, but let's see if we got the right value. -1, and then it was negative square root 15. I'll make this one a little bigger. There. So it popped it in right there. Okay. Last example before you get to do one yourself. All right, I'm going to change some of the notation up here. I want us to look at the function t of x equals the square root x squared, x squared plus 9 over 6 plus 8 minus x over 8. And I'd like for us to look at this on the interval 0, 8. Is that a continuous function on that interval? The only thing you have to worry about here is square root of a negative number. Is that possible? No. Any number you square and add 9, it's going to be bigger than 0. So you don't have to worry about negative numbers. There's no division by 0 here. So we are good, right? So continuous, closed. Okay. So I'm ready for the first step, which is take derivative. So I'm going to use t prime of x instead. Ooh, okay. Well, you know what? Let me get rid of the prime. Let me rewrite the function. How about 1/6 square root x squared plus 9 plus 1/8, or how about we split that second fraction into 2 pieces? How about we make it 8 over 8 and then make the other one negative x over 8? Is that okay? So it'll become 1 minus, instead of x over 8, I'm going to write 1/8 x. Because when you have a square root of a sum, you cannot do the square root of each one. It's only if you had a product in there. Ready? Derivative time? Okay, derivative of this thing here. 1/6 is just going to sit here. Times, what's the derivative of square root of something? 1 over 2 root of that something, right? But then you have to come through with the derivative of what's inside. So what's the derivative of what's inside the root? 2x? Are we done with that? Okay. Plus, what's the derivative of 1? 0. Minus, what's the derivative of 1/8 x? 1/8. So we need to cancel out some 2's here. Put the x on top maybe. I'm just cleaning up now. Right? You slid that x on top. Cancel those 2's out. And what are we going to do with this derivative now? Figure out where it's 0. Figure out where the derivative doesn't exist, right? Now, when you set that derivative equal to 0, I'm hoping it would be kind of natural to move the 1/8 to the other side. I'm going to skip the step where I write equals 0, and I'm going to just move the 1/8 over now. Is that all right? Y'all understand what I did there? So I keep asking. I don't think I'll ever stop. Sorry. Move that 1/8 over. Now I'm going to clear fractions. So let's get rid of the numbers. How about 6 and 8? What can I multiply both sides by to get rid of the 6 and the 8 at the same time? What's a common multiple of 6 and 8? 48, right? You can multiply both sides by 48. 24 is probably the least common multiple, right? No, that's the one I would want to go with. The least common multiple, but it doesn't matter. You'll get the same answer at the end. So multiply, what do y'all say? 48 or 24? I don't care. Do y'all care? No? All right. We'll go with 48. That was the first one. 48 on both sides. And then I'm going to multiply both sides by the square root also. So when you multiply the left side by 48 square root x squared plus 9 and 48 square root x squared plus 9, you get cancellation. 48 divided by 6 is, what do we got? 8. And then what's still there? 8 what? 8x equals, over here, 48 divided by 8, 6. And then you have the square root, don't you? This is what I taught my 0302 class last semester. Is called. I told them this is called a radical equation, right? A square root equation. And the way to solve a square root equation is to isolate the root and then square both sides of the equation. So you get the root factor by itself, and then you square both sides. So I'm going to go ahead, and I'll square both sides right now. Let's just do it. Square both sides. I'm doing this because I want to get rid of the root, right? I get 64x squared equals, I have to square the 6, 36. I have to square the square root. When I square the square root, it goes away. But I have to leave it in parentheses so that I can distribute the 36 through. Questions? I'll distribute 36 through now. What's that? 180 plus 54. What is it? Is it? Yeah. Wow. All right, now what? I'm out of room, that's what. How about we subtract 36x squared on both sides? So what's 64 minus 36? 28? 28. X squared equals 324. I'm going to run out of room, so I'm trying to keep this all on one page. Are y'all still there? Or? Okay, you are? You're here? Divide both sides by 28. X squared equals 324 divided by 28. Can we reduce that fraction? That's too big. What is it? 81 over 7? And now I'll take the square root of both sides. Plus or minus square root of 81 over 7. That's nice because I can take the square root of the top, that's 9. Square root of the bottom is root 7. So getting 9 over root 7 here. Plus or minus. Now remember our interval. What was our interval? 0 to what? 8? Only one of those is in between 0 and 8, and that's what? The positive one. So 9 over root 7. That's my only candidate for where the derivative is 0. Have you kind of noticed that there's every single one of the problems I've shown you today, the algebra for figuring out whether derivative is 0 is different? You know, I mean, that's going to be inherently the problem that you're going to run into because the book assumes that you are friggin' algebra masters. So I can show you 20 examples, but then you're going to do a homework problem and you'll be doing algebra that I haven't shown you. But it's assumed that you can do, which is, you know, that's just part of the challenge of this course. Now, t prime does not exist. We need to go back and look at this here. Where was my derivative? There it is, in the green box. The only thing that's going to cause a problem is if I get division by 0 there. But we already said x squared plus 9 couldn't be 0. So wouldn't you agree that the derivative is good all the time? Right? Nothing causes a problem. So it's not applicable here. Does not apply. So what's the only number I'm going to plug into the function to test here? 9 over root 7? And here I go. So I don't want f of 9 over 7. I want t of 9 over root 7. I said 9 over 7. 9 over root 7. And now I go back and I friggin' figure out where the hell t was. It's going to be the square root of 9 over root 7 squared plus 9 all over 6. I'm going back to like the original one. Plus 8 minus, are you serious? 9 over root 7 all over 8. Christ, I don't even want to touch that. I'm just going to say that this is approximately 1.33. I'm going to just, you know, you get on your calculator and you do it, and that's what you would get, okay? I'm not going to go through it. You understand you would have to do that on your calculator? All right. Now let's go and look at the second step, which is to evaluate the function at the endpoints, which were at 0 and at 8. And again, I'll save us some time. At 0, you get 1.5 on your calculator. At 8, you get approximately 1.42. Everyone understand I'm just saving us time by doing that for you? But you're just plugging those into the function. So where do you have a max? Where do you have a min? Max at 0, 1.5. And a minimum at 9 over root 7 1.33. Oh, jeez. Now you might be asking yourself, why the hell are we doing this, right? The answer is I don't know. No, I'm kidding. All right, here's a problem. I want us to see the value of what we're doing. So I'm going to give you a problem. We're looking a little bit ahead, but I think it's worth you seeing right now. So let's just say that we have a river that's roughly straight. This is a top view of a river, okay? So the blue, the water's in here, okay? I'm not going to put water. And what we have is we have a company that has a building at point A, and that they have a building down the river on the opposite side, point B, and that the distance downstream is 8 miles. Okay? And what they need to do, this company needs to connect these two buildings together so that they can share data. So they've decided that they're going to run some network cable from building A to building B, right? So they get some, you all understand what I'm saying? Okay, they have to connect them, however it is. And they get a company out here that gives them a bid of how much it's going to cost to run the cable. So let's say we're that company, okay? We're the company that's going to go out here and give them the bid. This is what the company wants. They want to go from A to B, 8 miles across the river. Oh, the river, sorry, I didn't give you how wide it is. The river's 3 miles. That's a pretty wide river, okay? Now, yeah, I know. This is all hypothetical, all right? Our company specializes in running network cable through water. Okay, we have a special cable that we can just lay in there. We just set it in the water. It's got a 50-year lifespan, whatever. This is all bullshit. I'm just making it up, all right? We specialize in that though, okay? Which is why they came to us. For us, the cost for running wire underwater is is 6,000. No, well, yeah, we'll just say $6,000 per mile. Now, when we get to the ground part, trying to do it on the ground, we run into more cost because we have to actually excavate, dig, bury. Okay, so it's a little more expensive if you want to run it along the ground. Okay, so it's $8,000 per mile to do it in the ground. Everyone understand the question? I mean the scenario. So underwater, it's $6,000 a mile. If I go on the ground, it's $8,000 a mile. What's the question that we're going to ask then? What's the cheapest way to run a wire from A to B, to connect the two? So let's just consider some possibilities here. I could just go straight across, right? And then straight down. That's one scenario, isn't it? If I do that, I'm going to go how many miles underwater? 3. And I'm going to go how many miles across down on the ground? 8 miles. So I'm going to have 3 miles at how much per mile? 3 miles times the 6,000 per mile, right? right? Plus the 8 miles at how much per mile? 8,000. Right? So how much would that be? What is it? 82,000. That's one way to do it. Here's another way. I could just go straight from A to B. Right? In that case, I'm going to go how many miles? So you'd have to get the Pythagorean, right, to figure out how long the purple is. So it's the square root of A squared plus B squared. So 9 plus, what is that, 8? Oh, 64. It's probably a nice number. No, it's not. So you get something like 8.544, something like that. That's how long that is. But it's all underwater, right? So what's the cost there? 6,000? 51,000. So I'll say in the purple, if we do the purple, it's 51,264, right? If we do the green, it turns out to be, what was it, 82,000? Yes, 82,000? So which one should we do? From appearances, the purple, right? But is there something in between those two that would be even better? Like maybe if we do a slight angle and we go across like this and then come the rest of the way on the ground, maybe that's cheaper. And it turns out there is a cheapest way to go. And it's something like that blue, that light blue. And believe it or not, it is the calculus problem that we just did. Okay? It's the problem we just did. We found the minimum value, right? Go back to the problem we just did. We found the minimum value of a function on a closed curve, right? Or a function on a closed interval. And we got this minimum right here. That actually is going to correspond to where we would have to aim our line to go underwater across the river. So I'm going to help just develop this function from that, and then we're not going to do any more. I just want you to see the correlation, then we'll move on. So back to this. Okay, for the sake of simplicity and making numbers look right, okay, I'm going to do a quick conversion. Instead of using $6,000 per mile, I'm just going to use 6 and 8 to represent 6. Everything's measured in thousands. So $6,000 per mile. All right? $8,000 per mile. Just get rid of some of those zeros. Is that all right? I'm going to redraw a picture here. River. Point A. Point B. We know it was 8 miles this way. We know it was 3 miles this way. And what I'm kind of guessing is that I'm going to be able to go across and then down, right? What I need to know is to figure out my total cost. It will be the cost in the water plus the cost in ground. Right? That's what it will be. So I need to know how long, I'm going to change this to purple now. I need to know how long that purplish blue is, right? Because I'll take that number and multiply it by what? How much are we charging to go underwater? 6. So I'll multiply it times 6, right? And then I need to know how long this yellow is. And I'll take that and I'll multiply that by 8. But the lengths, I don't know the lengths because I don't know where to go, right? Like I don't know where to aim it. So I'm going to come up with arbitrary numbers here. I'm going to create a little right triangle here. So my triangle looks like this. And I'm going to call the distance from here to here x. All right, so it's kind of like the guys are standing across the river at A. They look straight across and they go, okay, you guys on the other side, walk down X. That's where I'm going to aim, okay? That's X. Then how long is the rest of the way from that point down to B? 8 minus X, right? That's how long that would be? So like if X was 2, it would be 6 the rest of the way. If X was 3, it would be 5, right? If X is X, it's 8 minus X. How long is this side? Well, isn't that red right triangle, that's the hypotenuse, isn't it? What are the sides of that triangle? 3 and X, right? So if I call this side H, hypotenuse, we have that 3 squared plus X squared equals H squared. And therefore, the square root of 9 plus X squared is H, isn't it? Y'all still with me or not? Okay. So let's go back to that function. Where was it? It's not going to be exactly the same, but it'll be pretty close. Where is it? I lost my spot. There it is. No, it's further up. Okay, see that? Recognize this? We just got that, right? Recognize this, 8 minus X? The 6 and the 8 is like the money, the thousands of dollars. Now, this problem's a little different because I adapted it from a problem in the book just so our numbers would work out nicely. In the book, it's a person who's rowing across a river and then walking downstream. And they want to know, like, what's the shortest time if they aim across the river. But the derivative would pretty much work out the same, right? So we're going to spend, this is 4.5 optimization. We'll spend a couple of days on that. I just wanted you to kind of see, like, we're going to be able to answer some pretty interesting word problems using what we've learned today. All right? Okay, I think we're not going to get to mean value theorem today. What I'd like to do is give you a couple of problems to work on, and when you're done with them, you can show them to me and you can call it a day. That sound fair? Does every table have a book? Everyone, at least one person at each table? I'd like for you to do page 209. Let's do 41. $44. We have 30 minutes, right? And 49. All of these are just like what we just did. You can work together, all right? I believe those are 2 homework problems in there. Let's see, you're supposed to go and do through... Oh yeah, look everyone, scratch the homework from 4.2, okay? You don't have to do that for next time. We didn't cover 4.2. But the problems I just gave you are actually 2 of your homework problems. So you get started with them. Yeah, it looks like what we'll do is on Monday we'll do 4.2, and that will be the last topic that'll be on the test. 4.2. All right, I'm going to stop the recording real quick.